Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on single phase off-bridge inverter with RL load and RLC load. So series RL and series RLC load. Here the types of inverters means here voltage source inverter. Here voltage source inverter means output voltage is constant, independent of voltage, independent of load, whether it is R load, L load, RL load, RLC type of load. The output voltage is constant. And what about the current source inverter? Current source inverter means output current is constant irrespective of load. So that is current source inverter, that I will explain later. First, in the voltage source inverter, again two types, single phase and three phase. If you get the single phase output, so that is single phase inverter, and if you get the three phase output at the terminals output side, so that is three phase inverter. It is again off bridge and full bridge inverter. In the last lecture we discussed with R load and RL load. So today we are going to have a discussion on RL load, series RL load, series R and L. So resistor and inductor are connected in series, and next R, L and capacitor C, RLC elements are connected. So that loads we will discuss. So now here a single phase off bridge inverter circuit diagram already we have seen. Here we are changing only the load, RL load. Here for RL load, so first here the switching configuration, time duration. So here from 0 to T by 2 duration. So here 0 to T by 2 duration, S1 will conduct. So here minus VDC by 2 plus V0. So V0 equals to VDC by 2. And next here from T by 2 to T. So the duration minus VDC by 2 minus V0. So that equals to V0 equals to VDC by 2. So now here the switching configuration, so that I will explain. S1, D1, here 4 switches, RL load. For inductive load only diodes will conduct. So now here S1, D1, S2, D2, all 4 switches will conduct. So that here, so this is the circuit configuration. So now here output voltage waveform, output current waveform, and next switch current. So this thyristor current, and next here this diode current. So these 4 waveforms we will see first here. So now here these are the total time period is T. So this is T by 2, T by 4 and 3T by 4. So now here the output voltage waveform. So this is the VDC by 2. VDC by 2. From 0 to T by 2, this is VDC by 2, and this is the T, total time period T. So now here we are getting the AC waveform, positive and negative. Complete set of positive and negative is known as a, so that is AC. Here we are giving the DC input, but here we are getting the output voltage. So that is a single phase supply we are getting at the output terminal. So now here from 0 to T by 2, S1 and D1 will conduct, and from here from T by 2 to T, S2 and D2 will conduct. So that configuration we will see. So now here first if any DC supply is given to RL load. So now here you will get the output voltage waveform, the current output current waveform. So that is exponential. So if any DC excitation is given to RL type of load, so this is DC excitation is given to RL type of load. So this is circuit is closed. So that excitation is the exponential. So now here how you will get the exponential. So now this is the exponential. So so now here this is the exponential. So not like this. So this is up to pi. So this is a pi duration. In the pure inductive load, So that is triangular, so that is up to pi by 2, but this is the phi duration less than pi by 2 duration. So now here this is the exponential curve. After that, so it will decreases. So now here the waveform should be like this. So this is exponential, so this is up to pi. So this is 2 pi. If suppose t equals to 2 pi, so now here this is half t by 2 means that is pi, and next here this is pi plus phi. So now here this is pi minus pi. So now here this is alpha. So this is the phase. So now here this current, this switch output current lags voltage by this output current I naught of t lags V naught of t by phi angle. So this is 5 degrees, phi angle. So now here 5 degrees means here in case of pure inductive load, so that is pi by 2. So that is up to, that is triangular waveform. So now here, so how in which duration D1 will conduct, in which duration T1 will conduct, S1 will conduct, in which duration S2 and D2 will conduct, that I will explain. So now here is this during 0 to pi. So 0 to pi, 0 to pi duration, which switch will conduct. So 0 to pi, current is negative and voltage is positive. So current is negative, voltage is positive means for this 0 to pi duration, so D1 thyristor will conduct. So here D1, let me change the color over here. So here D1 thyristor will conduct. And next case here, so here voltage is positive and current is positive. So this is the here in between this. So here pi to pi duration, phi to pi duration, here S1 thyristor will conduct, S1 switch will conduct. And next here, so voltage is negative and current is positive. Voltage is negative and current is negative means, so for pi to pi plus phi, pi to pi plus phi duration, so here D2 will conduct, this D2 will conduct. And next here voltage is negative and current is negative means here S2 thyristor will conduct, S2 thyristor. So here here pi plus theta 2 and 2 pi, so up to here, so T2 will conduct, S2 will conduct. So this is the switching time duration for here 0 to pi, D1 thyristor will conduct, and phi to pi S1 thyristor will conduct, and pi to pi plus phi D2 thyristor will conduct. And next here pi plus theta 2 and this 2 pi, so here S2 thyristor will conduct. So now here what about the switching? So here this is the, so this is the switch time S1, and next here S2, and next here this is the D2 diode currents, and these are the diode currents. So now here this is one D1 and D2, D1 and D2. So these are the diode waveforms, and these are the diode current waveforms and switch current waveforms. And next here total output waveform. So this is the configuration. So now here what about the RMS output voltage? RMS output voltage here, RMS output voltage is already we have seen this output voltage for any type of load. So here for voltage source inverter, so the output voltage is same irrespective of load for R load, L load, RLC load, RL load. So here this output voltage is fixed, but current only changes if you change the load only. Here this output voltage is fixed. So in the previous case also we got total output RMS voltage equals to VDC by 2. And next output voltage in the Fourier series, so that is this one is So this voltage is always peak value of fundamental. So this is the Fourier series of output voltage, that is n equals to 135 n sigma, and now here 2 VDC by, actually this is 4 pi by n sin omega nt, but here Vs equals to VDC, 2 VDC by 2, that means 2 VDC. So that already we discussed. But here this current waveform, here this current, here what about the fundamental V01, V0 fundamental output voltage equals to, that equals to sigma. Let me change the color over here. So sigma n equals to 1 to 135 to n 2 VDC by n equals to 1. So that is pi and sine omega t. Here n equals to 1 for fundamental output voltage. So that equation Fourier series. So any square wave or any periodic wave is resolved into the series of sine waves with different frequencies. Here is the first frequency is the fundamental output voltage. So that is, so this output voltage peak value is always greater than this total output voltage. So now here what about the current? So now here current waveform I am drawing here. So this is the current waveform. So this is pi and this is the phi, and this is the pi, this is the pi plus phi, and this is the 2 pi. So now here this is the 2 pi. So now here this current lags this voltage by this phi duration. So this is 2 VDC by n pi, and this voltage divided by this impedance. So always I naught equals to V naught by Z. So this is the Z divided by Z, and it lags current. This current lags voltage by this phi duration. So this is the phi minus phi. So now here I naught of t. So now this I naught of t equals to sigma n equals to 135 n. So now here 2 VDC by n pi Z sine n omega t and phi. Here phi equals to, what is the phi value? Tan inverse omega L by r. And what about the Z equals to square root of r square plus omega square plus L. So here omega equals to 2 pi f. So this is the formula. Already we know very well about this. Already we have studied in the single phase circuits. So now here each thyristor. So each thyristor is conducting up to what duration? So this is the S1 thyristor will conduct. Let me change the color over here. Here S1 thyristor will conduct, and here D1 thyristor diode will conduct. Here D2 will conduct, and here S2 will conduct. So now here during this period pi minus pi and 2 pi minus pi minus pi. So S1 is conducting for pi minus pi, and S2 is conducting for 2 pi minus of pi plus phi. So that equals to pi minus pi. Each thyristor, each switch is conducting up to pi minus pi. But here total, what about the total switch current? So total conduction time for total thyristor switch is 2 into, here we have 2 switches means multiplied with 2 into pi minus 5. And next, what about the diode conduction time? Is this is a pi duration. This pi duration, so that is a phi. Each diode is conducting. D1 diode is conducting for pi duration, and next D2 diode is conducting. D2 diode is conducting for pi plus pi minus phi, that equals to phi. So each diode is conducting for pi duration only. And next, what about the total diode conduction time is 2 pi plus alpha. And now here total fundamental component of, so now here how we will calculate the fundamental component. Let me change the color over here. Integrate IT of 0,1 average value and IT of 0,1 RMS value, and IT of 0,1 ID of diode current average value and ID of 01 RMS value. How you will calculate this one? So here it is conducting up to what angle? So let me change that. So here, so first IT off. So it is conducting up to what angle? So from pi to pi plus alpha. This duration it is conducting. So in the 2 pi duration. So now here, so this equals to 1 by 2 pi. Total time period is 1 by 2 pi. So that equals to 5 to pi only. 5 to pi. So what about this equation? This equation is important, that is d omega t. So this equation is, so that is I01 maximum value sine omega t. So here n equals to 1, that is fundamental, and I01 maximum sine omega t minus 5. Sine omega t minus 5. And next here, under root 1 by 2 pi, so that equals 0 to 5 I01 maximum sine omega t minus 5 whole square into d omega t. And next here, diode RMS current equals to, so diode, this is up to, if suppose it is conducting, this is a phi duration and this is a pi duration. From 0 to pi, S2 will conduct, here D1 diode will conduct. So now here this duration, so here these two formulas for this duration. So up to this duration, so phi to pi, so this is these two are conducting. And now here for this one, here diode average value equals to 1 by 2 pi. It is conducting up to what angle? From 0 to pi. So here 0 to pi. So the equation is same, I01 maximum sine omega t minus 5 d omega t. So now here this ID RMS equals to 1 by 2 pi, 0 to 5 I01 maximum, 01 maximum sine omega t minus 5 whole square into d omega t. So not this is 0 to 5, not pi. This is a 5, and here is also 0 to 5. These limits are most important. From 0 to 5, diode will conduct. From pi to pi, thyristor will conduct. But here we can't judge this I01 maximum. How we will judge this one? So in the previous case, in the diode, in the previous case, here in the sine wave, we can judge this. We cannot judge this exponential, this maximum value. Here I01 maximum, just keep it as it is formula. So now here IT01 average equals to 1 by 2 pi 5 to 5 I01 maximum sin omega t 5 d omega t, and IT01 RMS equals to under root 1 by 2 pi 0 to 5 I01 max sin omega t minus 5 whole square d omega t. ID01 average value equals to 1 by 2 pi 0 to 5 I01 maximum sin omega t minus 5 d omega t. ID average, ID a diode, fundamental diode RMS value equals to under root 1 by 2 pi 0 to pi, and 0 I01 maximum sin omega t minus 5. And now here, what about the fundamental displacement factor? So there is an angle between that, that is phi, angle between voltage and current. So here there is an angle between, this is the current and this is the voltage. There is an angle between voltage and current is the phi, that is phi. And next here, fundamental total power across load due to the fundamental is P01, V01 RMS and I01 RMS. This is a cos phi, this cos phi. And total reactive power across the load due to the fundamental is the, so that is sin phi. We know the P equals to Vi sin cos phi, that is active power, true power, and Q equals to Vi sin phi. So this already we know very well. in the single phase circuits already we discussed. So now here what is the conclusion here? For any type of load, here for any type of load, the output voltage is for any type of load. So for any type of load, here for any type of load, output voltage is constant. For any type of load, output voltage is constant. So now here our output voltage Fourier series equation, output current Fourier series equation, each diode and each thyristor conduction time, and total thyristor and total diode conduction time. And next, in which duration D1 thyristor will conduct from 0 to pi, and S1 thyristor will conduct from pi to pi, and D2 thyristor will conduct from pi to pi plus phi, and S2 thyristor will conduct from pi plus phi to and 2 pi. So these are the IT01 fundamental component of thyristor, average value, RMS value, fundamental component of uh, diode current, average value, RMS value, fundamental displacement factor, total power across the load due to the fundamental, reactive power across the load due to the fundamental. And next here for RLC type of load, how you will calculate the how you will so here RLC, here I am changing the output voltage. So here RLC type of load, in the previous lecture we have discussed R type of load, but here RLC type of load. Here same, here from 0 to pi by 2, so that minus VDC by 2, and V naught here from pi by, so V naught equals to VDC by 2, and pi by 2 to T by 2, next of duration minus VDC by 2, 0 to, this is for 0 to T by 2, and this is for T by 2 to T, and next this one equals to VDC by 2. This already we have discussed. And now here this is a switching configuration in the RLC type of circuit, so that we will see. So now here this is a output voltage and output current. So now here first, output voltage is constant, always fixed. In case of voltage source inverter, output voltage is constant. Even though if you change the load may be R load, RL load, RLC type of load, RL type of load, that output voltage is fixed, we cannot change, but current will change. So in case of RL load, R load, so that is square waveform, R load. For L load, that is triangular waveform, and for RL load, that is exponential. That is exponential. For RLC type of load, that is sine wave. Sine wave. If you give any DC excitation given to the R type of load, that is always a square wave, and if you give any DC excitation is given to pure inductive load, that is triangular. So this is a square, this is the triangular, and this is the exponential, and this one is a sine wave. This much is clear. So this is for R load, RL load, L load, and LC load, R load. And now here this phi value is 0. Here phi value equals to 0, and here phi value equals to 90. Here phi value equals to some angle, and here is also phi value equals to some angle. So now here we have two types of sine wave. If you we are giving the DC excitation is given to RL type of load. Here your output current is the sine wave, sinusoidal waveform you will get. How you will get? Same as so here in the previous case. So this is the sine wave. So not like this. Here like this. So one, So like this is sine wave. So in the RL type of load, you got one exponential waveform, but here is the sine wave. So this is for when RL is, so when XL, inductive reactance, is greater than XL is greater than XC case only. And now here, what about the XC is greater than, so in case of R, L and C, sometimes XL or XC, sometimes X may be a greater than XL, sometimes XL is greater than XL. So for that case, so that two conditions I will explain. So now here, this is the phi. Let me change the color over here. This is the phi duration, and here up to this angle, so that is pi. So this is the phi duration pi, this is the pi plus phi, and this is the 2 pi. So now here d same as it is, this is positive and this one is negative. So here 0 to phi duration d1 thyristor will conduct, and next from pi to pi. So now here phi to pi duration S1 D1 diode will conduct here, and S1 thyristor will conduct, and here it is positive and here it is positive. And next case here, what about this one here? This is voltage is negative and current is positive, means here pi to pi plus phi. So now here D2 will conduct, and next here this one, both are in negative voltage and current, this is the S2. So now here pi plus phi to 2 pi. So now here, this is the sine wave waveform. The time duration for each switch and voltage is negative and positive, and current is negative and positive. And if suppose what is the if suppose this is the overdamped case, and here zeta is greater than 1. And next here, for underdamped case, XC is greater than XL. So for that case, I am drawing the waveform. So now here, same pi duration, and here pi duration. Here, this one. Here D1 voltage is positive. Here S1 will conduct. Both are positive, means here S1 will conduct. Sorry, the diagram may be like this. Here here like this. Sorry. This is the case. So now here current lags voltage by, here in this case. So in this case, let me change the color over here. In this case, V0 or I0 lags V0 by phi angle, but here I0 leads V0 by phi angle. This is the phi angle. Here S1 thyristor will conduct up to this one. S1 thyristor will conduct, and here D1 thyristor will conduct. Here both are negative, means here S2 thyristor will conduct. Okay, and next here both are in negative. So now here and here D2 thyristor will conduct. So one is positive and one is negative. So this is the waveform. So now here, this is important. This is the overdamped case. This is the underdamped case. Underdamped. So here XC is greater than XL. So now I'm explaining again. So here output voltage is constant because it is a voltage source inverter. It is this output voltage is fixed for constant for all loads, R load, L load, and RL load and RLC type of load. This is same for all type of load, but only current will changes. For R load is a square waveform, for L load is triangular, and for exponential waveform, for RL load exponential. For RLC type of load, here it is a sine wave. So the angle is 0 here, and the angle is 90, the angle is phi, and the angle is phi. And now here, this is the sine wave here. So this is, here we have two cases. One is x, sometimes XL is greater than XC, and in some cases XC is greater than it. So here I am drawing two current waveforms. For XL is greater than waveform, this is sine wave. So here when a DC excitation given to the RL type of load, you will get the sine wave. But here we have two waves. So XC is greater than XL case and XL is greater than XC case. So now here this is the case. So this is the case. So now here this is the angle phi. So this current lags voltage by 5 degrees. But here in case of XC is greater than XL, so in the current leads voltage by from some angle phi. So now here which the from 0 to pi, so which thyristor will which switch will conduct, this is positive and negative. So this D1 will conduct, and phi to pi, and this positive and positive S1 will conduct, and this is negative, and this one is the positive, and this D2 will conduct, and this one is in the both are negative, means S2 will conduct. But here in case of underdamped case, XC is greater than XL case, so both are positive, means here up to this 0 to pi duration, phi S1 will conduct, S1K will conduct, and again this one. So this is positive and this is negative, and here during this period the D1 will conduct, and both are is negative. So now here S2 will conduct, and next here some phi to pi plus phi, and next pi plus phi to 2 pi D2 thyristor will conduct. So these are most important. But here one important thing is, here in the underdamped case, self commutation is possible. For overdamped case, forced commutation. But here in case of underdamped case, let me change the color over here. So now here in the underdamped case, self commutation is possible. Commutation is possible. So how it will happen? So here S1 will conduct up to from 0 to pi. After pi to pi plus phi, D1 will conduct. If suppose it is 1 volt voltage. So now here, so this voltage, so this is plus and minus. So it is connected across this SCR. So this SCR is, it is bidirectional. So it is like this. So now here this negative voltage and is applied across this SCR. So here we are applying the reverse potential to this, and now here reverse potential means here this SCR will be turned off. Here in case of RLC type of load, XC is greater than XL, self commutation is possible. Underdamped case means zeta is between 0 to 1. So this is most important point. And now here that RMS output voltage is this one, and here V0 equals to, already we have discussed, N equals to 135 N 2 VDC by N pi sin omega t. But what about the current? So V0 by Z I0 equals to, this is a Z and this is a phi angle. If it is a leading load XC is greater than XL, that is plus. And next here conduction time for each thyristor pi minus phi, each diode is phi, and conduction time for total thyristor is 2 into pi minus phi, and conduction time for total diode is 2 phi. And now here, so this is phi equals to, what is the formula? So now tan inverse, so N into omega L minus, so 1 by n into omega C divided by R. And next here, what about the Z equals to R into R square plus omega n into omega L minus n into omega C whole square under root. So this is 1 and this is 2. Here Z equals to, and this is the phi equals to. And now here that fundamental displacement factor and total power across the load due to the fundamental, total power across the load due to the fundamental. So P01 and Q01, V01 RMS and I01 RMS cos phi, and V01 RMS and I01 sin phi. And next here total IT fundamental switch current average value, that equals to 1 by 2 pi, already we discussed in the R load. So that is 0 to pi to pi I01 sine of omega t minus phi. So this is a maximum value d omega t, and IT01 RMS value equals to 1 by 2 pi integral of phi to pi I01 maximum sine of omega t minus phi whole square d omega t under root, and ID01 average equals to 1 by 2 pi. So that is conduction time is 0 to this phi duration, not pi, 0 to phi I01 maximum sine of omega t minus phi d omega t. And next ID01 RMS value equals to 1 by 2 pi under root 0 to phi I01 maximum sine of omega t minus phi whole square d omega t. So these are the formulas. Now here I hope all these concepts are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.